Okay, let's work our two inelastic collision examples here. And the first example, we have a skater that jumps into the arms of the other skater, and we're asked to calculate the final velocity of these two skaters that are now stuck together. Okay, so for these types of collision problems, it's best to draw an initial situation and then the final situation. So here's our initial situation. We have our, and I'm just going to draw our skaters as circular, just because it's easier. We have our 60 kilogram skater, who's going at 4 meters per second, okay? Jumps into the arms of our stationary 75 kilogram skater. And so that's our initial situation here. Our final situation, our two skaters are now stuck together. So there's our final situation. And they're cruising along now at some final velocity that we need to solve. Okay? Now conservation of momentum says our initial momentum has to equal our final momentum. Momentum is given by momentum of any object is the mass times velocity. So therefore, the momentum of skater 1, we'll call this one skater 1 and this one skater 2. The initial momentum of skater 1 plus initial momentum of skater 2, that's our initial momentum of our system. And that has to equal the final momentum of our system. Okay? The initial momentum of skater 1 is the mass times velocity. So it has a mass of 60 kilograms, velocity 4 meters per second. Now skater 2 is stationary. Okay? So 0 velocity means 0 momentum. And this has to equal our final momentum. Now our final momentum is a little easier to calculate. We just have now one object. That is, our two skaters are now stuck together. So the momentum of this one object is the total mass, 60 plus 75 is 135 kilograms, times the final velocity. Okay, this is a fairly easy algebra problem to solve. 60 times 4 is 240, divided by 135 gives you that velocity, which we were trying to find, 1.78 meters per second. Okay, so our joined together skaters are now cruising down the ice at 1.78 meters per second. Okay, and again, this is the big advantage of using momentum to treat these types of situations. We're not concerned at all about the actual forces that are exerted between these two when they collide. That would be a fairly complicated type of thing to study. All that matters is our initial situation and final situation, because momentum is conserved for isolated systems like this. So we don't really care what happens inside of our system here. Our system consists of these two skaters. It doesn't matter what's going on inside. All that matters is the momentum of that system before and after. It really simplifies these types of problems. So let's work the second momentum inelastic collision problem. Okay, and in this problem we have a spring-loaded gun. So our initial situation, and we'll try to be as artistic as possible here with our gun. So there's the gun, and we have some ball in here. So here's our initial situation. We have a spring-loaded gun. Now our final situation, well, we have our gun, which is recoiling at some final velocity that we're trying to find. Okay? And our ball is now moving on this way at, what's the number, 15 meters per second. So this is basically very similar to the problem we just did. it's not a collision. It's basically a perfectly inelastic collision in reverse. So if you play this backward in time, the ball and gun will eventually join together and stick together. And we'll have this situation. So mathematically, you can treat that exactly the same as an inelastic, perfectly inelastic collision, like the skater problem we just did. Okay, so again, momentum of our initial situation has to equal our system's final momentum. So our initial momentum, here we have some initial momentum for our gun plus ball, and that has to equal the final momentum of the gun plus the final momentum of the ball. Okay, so what's our initial momentum? Well, our gun and ball are stationary. So our initial momentum is 0, since there's 0 velocity there. Now, the final momentum of the gun is the mass of the gun, which we are told in the problem is 1.2 kilograms. Because remember, momentum is mass times velocity. So 1.2 kilograms times our final velocity plus the mass times velocity of the ball. The ball's mass is 30 grams, but we want to get into kilograms because our gun mass is in kilograms. 30 grams is 0.03 kilograms. And our ball's velocity is 15 meters per second. Okay, so we do this problem, 15 times 0.03, subtract that from both sides, and then divide by 1.2, and you find that the final velocity is negative 0.375 meters per second. Okay, and again, that's basically what we'd expect. We defined to the right as a positive velocity, and the gun recoils to the left. So that's a positive velocity, therefore our gun has a negative velocity. And it's a relatively small velocity. Okay? So you can imagine with a more powerful gun, you're launching bullets at much faster than 15 meters per second. You're talking hundreds of meters per second. Bullets way less than this, but not a whole lot less. So you can imagine the recoil is in a real gun is considerably larger than this number right here.